I'm going to say ALPyNA, but never mind. I don't think it matters really, does it? Good. So, hello, vastly reduced audience. This is a talk about Python, and really all the work was done by this PhD student here, but he's just had a baby, or his partner's just had a baby, so he's not here. But I am instead, never mind. So, first of all, right, if you Google ALPyNA, the first thing that pops up, at least in my filter bubble, is shoes. But this is not a talk about shoes. And the second thing that pops up is cars. This is not a talk about cars. Instead, it's about accelerating loops in Python on novel architectures. Accelerating loops here means parallelization, vectorization of loops. And novel architectures, as far as I'm concerned today, just means GPUs, but it could mean something else in the future, other kind of accelerator platforms. I don't think this is controversial. You can throw things at me if you think it is. Python is one of the world's most popular languages. And there are lots of different programming language popularity charts. And this is the TOB index. And they have Python as number 3 and rapidly climbing in the charts. Okay, this is the IEEE Spectrum ranking. They have Python as number 1, and it's a bit like university league tables. You kind of pick the one you want that puts your institution at the top. So I'm going with this one here. Python is the most popular language in the world, with a ranking, presumably some kind of normalized ranking of 100, whatever that might mean, I don't know. They look at job adverts and GitHub commits and things like that. But there we go. Python is a very popular language. Oh yeah, so here is on GitHub, right? Apparently Python is the 3rd most popular kind of project on GitHub this year, and has been for the last few years, just behind Java and JavaScript. So Python is very much the language of the people. You might turn your noses up at Python, but you know, archaeologists, zoologists, and everybody in between writes in Python. This is true. If you check, there are libraries for archaeology in Python, ArchaeoPy, and I'm not quite sure what archaeologists do with Python, but they do something with it anyway. And here's an article from The Economist. Python has brought computer programming to a vast new audience. End users code in Python. When's this article from? 2018, so just last year. Novice programmers use Python as well, so this study was done a couple of years ago in British universities to have a look to see what the most popular CS 101 programming language is, and surprise, surprise, oh it's Java, oh dear, Python's the 3rd most popular language. I think there is somebody here from Edinburgh. Who's here from Edinburgh? You use Haskell, so hats off to you, but never mind. Nobody else does. And here's another slightly ridiculous chart showing that Python's the most searched for language on Google, apparently. That's from The Economist as well, so they know about it. So, right, what that slightly humorous slide is saying is Python is popular. You know, people are using Python, so this is a target for parallelization that can have a big impact in end-user programming communities. As well as Python being popular, so too are accelerator platforms. So we can see here, for instance, that there are lots of different kind of accelerators. There's some kind of NVIDIA GPU, and there are lots of different NVIDIA GPUs, all of which are used for gaming, but also for, you know, CUDA code as well. And oh wow, here's an FPGA which is purpose-built for Python, apparently. I'm not sure what that means really, but it's pink, and you can get one of these for not too much money and run your Python code on it in some kind of FPGA environment. And you know, if you can't afford an FPGA, you can rent one from Amazon. So FPGAs are now kind of commodity rentable items, and there are other things as well. This is a Google Tensor processing unit. These days. Okay, so crash those two things together. Python is populator, accelerators are ubiquitous, popular and ubiquitous, and you get kind of, you know, the recipe for people wanting to improve the performance of their Python code. Because, sadly, Python programs don't run quickly. So you might have seen this. This is the programming language shootout website here, and in a slightly unscientific way they look for fastest programming languages and they run lots of micro benchmarks, and here's the n-body planetary simulation in C. It takes 7 seconds. In Python, oh dear, it takes 100 times as long and seems to consume 1,000 times as much memory. So Python is not efficient. And there's another, oh, there's computing a mandelbrot set thing there, and again that takes a lot longer in Python than it does in C. And if you Google Python slow, you get 52 million results. You don't get as many if you Google Fortran slow, but never mind, maybe we need to normalise that. But Python's definitely kind of got this reputation for being slow, and the reason is, oops, my slide's a bit dodgy there, let me just fix that slide, I'll get that there, oops, try again. Good, right, so Python's slow because it's got a global interpreter lock, which means you can't really do things in parallel very quickly, but also because it's just in an interpreted runtime in general. There are more efficient, high-performance versions of Python that do some kind of just-in-time code generation. So the PyPy runtime for Python does just-in-time compilation to native code, and the number library also does JIT-ing for Python code. These generally just do sequential or SIMD style optimizations, but really to get high performance these days we need to use our multi-core resources, and that's difficult to do with the global interpreter lock in Python. But abstracting away from the implementation specifics of any one Python runtime, is Python a good candidate for parallelization? And I'm going to argue yes, it is. So, the control flow structure of Python code is generally quite simple. Okay? You can't do go-to in Python, isn't that nice? It has an explicit range function which you use to do a kind of counted, iterated loop, and you can't update your iterator variable in the middle. You know when you start the loop how many times you're going to go around it. You can't alias the iterator variable, and it's a good candidate for parallelization because the baseline performance is shockingly poor, so you're bound to do better than it. You see these things where people show you wonderful scaling, but then if you compile the thing in GCC-03 it runs super fast. Well, here our baseline performance is absolutely terrible, so we're going to be better than that when we parallelize, aren't we? But here's some reasons why you might not be able to parallelize in Python, okay? It's a dynamic language. You don't know what your data types are until you're actually running the code, and they might even change under your feet. And also, well, this is true for any language really, you don't necessarily know kind of loop bounds and sizes until the runtime. Okay, so this is what we did. We did classic dependence analysis, the kind of thing that auto-parallelizing Fortran compilers did in the 1990s, with some standard dependence analysis and tests using this textbook here as our archetype dependence analysis implementation. But that's all kind of, stuff that people did 20 years ago, right? Our novelty is we are staging the dependence analysis. So it's split over an ahead-of-time analysis phase and then a runtime phase. The ahead-of-time analysis is done when the source code is first introduced to the virtual machine, when you import the module or load the library or whatever. And then the just-in-time stuff happens when you invoke the code, and that's when you can resolve your data types and your loop bound and so on by runtime introspection. So the architecture here is split into two parts. This is the ahead-of-time part on the left, and that's the just-in-time part on the right-hand side. And you'll see that basically they both have the same kind of structure. We do some kind of dependence analysis and parallelization based on the results of that dependence analysis, and we do as much as we can ahead of time, but we sort of save partial dependence analysis, we cache that, so that at runtime we can come back. This just lives in the memory of our Python interpreter, and then at runtime we can kind of fill in the blanks when we know our loop bounds, we can make the dependence more precise, and also fill in the blanks for the types as well. So, in terms of the data structure, this is all coded in Python itself, and we use the Python AST library to parse the source code, and we build a set of loop landmarks which show us the nested control flow structure of our loops. Then we do the analysis on the NumPy arrays or Python lists to find the dependence relationships between the subscripts. And then we can generate, it's not OpenCL, it's CUDA, CUDA kernels, because we're running on an NVIDIA platform here. CUDA kernels with holes in for the kind of stuff that we don't know at compile time and need to fill in at runtime. So these are the novelties. It's staged, do some at compile time, some at runtime. It's all done in Python using standard Python libraries. At the moment we're running with CPython, the standard Python interpreter, but this could be extended to other Python runtimes like PyPy or other Python environments like interactive notebooks and so on. And when you find a loop nest you can parallelize, you put that into a distinct namespace so that the programmer or the runtime can either invoke this parallelized code or the original sequential code, and you can select between them at runtime. I'm going to tell you a bit about the benchmarking that we did now. So we used a fairly standard hardware platform here with a low-end GPU these days, I suppose, NVIDIA 1060, running on Linux and CPython, using this number library here, which is the thing that actually does the code generation to CUDA, and there's our CUDA toolkit version there. So we looked at 4 micro benchmarks here, which you'll see popping up in any kind of parallel prototyping paper here. So there's a matrix multiplication, vector addition, some kind of constraint system there, and a stencil computation, which is an implementation of Conway's Game of Life. So this is what the code looks like, and the thing to take away from this slide is this is ordinary Python code. We haven't done anything special here. This is just standard Python code. Admittedly, there are some restrictions on the kind of code that you'll find in this loop nest here, the body of the loop nest. But this is just the kind of code that you would expect end-user programmers to be executing. And when we run this through our ALPyNA system, we end up with CUDA kernels, which we can execute by offloading them to our GPU. Right, so to be honest, I'm not entirely convinced about these graphs, and maybe you won't be either. So the thing to notice is that for each of the sizes of input, there are 2 results reported here. The blue result on the left is the time that the benchmark takes when you execute it in the Python interpreter, the standard CPython interpreter, and then the kind of stacked bar on the right for each input is the time that's taken for our new system, the ALPyNA system. Right now, the y-axis is log scale, which means the stacked bar chart's a bit dodgy, really, but never mind. Just don't worry about that too much for now. Look at the kind of the top number there, and you'll see that in each case for this naive matrix multiplication, our code execution environment takes less time. The blue, red and green tricolor bar is always lower than the sky blue bar there, which means we always win for these particular iteration sizes. That's not always the case. So here is another benchmark here where, what's this? This is vector multiplication here. You'll see that the sky blue bar, which is the standard Python interpreter time, actually wins. It's a lower execution time until we get to larger iteration sizes over on the right, where we've got bigger input size, and there our code executes faster on the ALPyNA GPU system. So there's a kind of crossover point. Where's the crossover here? It's at there, isn't it? That third set of bars where the GPU execution is better than the interpreter execution. There are overheads basically, and the overheads are the blue. You can see them better on this one, I think. The blue and the red bars. So these overheads for doing the analysis, the dependence analysis, the compilation, which is effectively the GPU kernel turning from a string into CUDA PTX code to execute on your hardware, and then the dark green bar is actually execution time. And of course, because it's logarithmic, you can't really compare these things in their stack bar chart. But if you do it in the linear scale, then basically the light blue bar is whoop up there and everything else is minuscule down the bottom. What you can see here on the right-hand side is that we're 1,000 times faster with our GPU offload than doing the thing on native interpret Python. Yeah, and here's some more complex codes here. And again, there's a crossover point beyond which it takes longer on the interpreter than it does to do the GPU execution. You see that the analysis and compilation time, which is independent of the input really, is a constant. There's only this GPU time here, which is the execution time, which is growing. I mentioned there are some restrictions on the code you can have in your loop nest. At the moment it's only straight line code, so we need to implement some more, again, classic parallelization of if conversion to allow us to do control flow divergence, if else's and so on inside our loop bodies. We need to implement more complex dependence tests for multiple induction variables in our loops. And we can't actually do function calls within the loop body because we haven't got any side effect analysis that's interprocedural. None of these things are, beyond the realms of possibility. It just takes a bit more work, perhaps, to implement these. Right, so how else might you parallelize Python code? So, lots of people just use libraries that do the parallelization under the hood for you. So if you're running OpenCV or the scikit-learn machine learning library, then they'll do parallelization, but they do it in the kind of C code which your Python is wrapped around. So that's sort of native parallelism that's happening inside the library. Sometimes you might use DSLs to do GPU offload. There are things that will allow you to write your OpenCL or CUDA kernels inside Python and then compile them on the fly and run them. They don't do any dependence analysis or checking. And then there's something called Loopy, which is a nice DSL, which was presented, I think, at the Array workshop several years ago. If you have a long memory, you might recall that. But again, it's quite an esoteric, domain-specific language that you wouldn't expect end users who read The Economist or whatever to be able to write in. You could create task graphs that can be executed in parallel. I suppose TensorFlow does that kind of thing. Or you can look for functional patterns like maps and reducers and so on that are going to be implicitly parallel and parallelize those. So these are all other ways to do parallelization, but I'm arguing that end users aren't necessarily going to be able to do these things. Well, maybe the top one, but then that's only relying on particular libraries rather than being able to write your own code. So, there's still some work to be done here, and one is, do you remember in those graphs there was a crossover point beyond which the interpreter was slower and the jittered GPU code was faster? And what you might want to do is have some kind of runtime switch that says, this NumPy array looks big enough, I think we will do the GPU execution for this, and this one looks quite small, let's stick with the interpreter. So we can dynamically select which target code we want to execute. And indeed, it might be that we want to target other novel architectures like FPGAs or TPUs or whatever, and we might need to have other backends in different namespaces and kind of switch between those as well. This is all future work. So, here is my concluding slide. ALPyNA is a parallelization technique for plain old Python loops, such as you might expect end users to create. And this system here, I'm arguing, is going to make them more productive because they don't need to learn DSLs or look at particular libraries. They can just write ordinary Python code and reap the benefits of Moore's law and produce parallel executing code. It's portable. They're only writing ordinary Python, so they're not looking at the specifics of the GPU that they're running on or the other architecture. And if the code won't run on the GPU, then we can just fall back to the interpreter and the same code will run on that as well. And our dependence analysis is improving on the existing state-of-the-art dependence analysis that you might find in your Fortran compiler. It's the same kind of techniques, but this is staged, and we're doing some of it at compile time and some at runtime using the introspective capabilities of the Python interpreter to resolve these loop bounds, to simplify the dependent structure, and also to unpick the dynamic types. Good. If you would like to use ALPyNA, it will be appearing on GitHub real soon now. That's the end of my talk. Thank you.
Any questions?
How would you see implementation right now at reusing the generated code? So you have your function, right? We've done the work for one run, basically. I mean, we saw most of the time was the compilation time, so if you can reuse that, essentially you're always faster, almost always faster than the native code. But then the changes if the data switches a bit, right? The type switches, obviously you have to redo it, but also for the size. But for some sizes you may be able to reuse it still. What does it do right now? Does it only pick the precompiled version if it's exactly the same data and exactly the same size?
So at the moment, right, if the input is too large, then we don't actually know about that. We just give it to the GPU and we get a runtime error, and then we have to fall back to the interpreter. So we're only worried if the type changes, and then we do recompile the code, as you say. Yes. So we sort of cache the kernel for future invocations with the same types. Yes.
So how does it compare to C?
That's an interesting question. So if you run this code, or well, this Python code, if you translate it to C and run it there, do we get a performance improvement? I don't know. That's interesting. We do get an improvement over PyPy, which is the sort of jittered code that would compile to native code, so it does do better than PyPy. I don't have those performance stats with me here, but we certainly win, not by margins as large as we do for the interpreter, of course. Yes, I should do a C comparison to be unscientific like the computer languages benchmark game people. Yes, thank you, that's a good suggestion.
So do you do additional transformation before you do the parallelization? Because I noticed that matrix multiplication you have is fantastic, but...
Yes. So actually, in matrix multiplication, you'll notice that we've interchanged the loops there. Where's it gone? So actually, the K loop, which should be on the inside, we've switched it to the outside base. So yes, we do. There are some of these loop transformations, again, which are taken from the Allen and Kennett textbook, which we implement inside our runtime compiler. Yes, that's right. We haven't done too many of them, so we're not doing things like loop fusion, for instance, and there are more that we could do. It just depends on, I suppose, kind of programming effort as to how, PhD student effort as to how many we do. But yes, there's certainly possibilities there. Thanks.
I'm interested in the just-in-time compilation system. Since most of the time overhead was for compilation, have you considered any background type just-in-time compilation while you can compile in the background?
That's interesting. So could we sort of offload the compilation and carry on running? Yes.
Continue with the
interpreted code we could do. We don't at the moment, but that is that is a possibility. Yeah, at the moment we sort of oh dear, stop the world, do the CUDA compilation and then start again. Yes, yes. But you're suggesting we could do something more sophisticated, like run the interpreted version until the CUDA version is available. Yes, yes, that's a possibility. Thanks.
How do you make decisions about the size of the grid or the block, the different blocks, and so on and so forth? How do you decide about those aspects?
Yeah, so at the moment, we've only run this on a single GPU, and effectively we've hard-coded the sizes for that GPU. So if you were to run this on a different platform, then you need to tune those heuristics effectively for your new GPU. So it's not, it's tied to the performance is relative to the GPU on which you're running. Yeah.
Maybe a follow-up question. What about the data? So for example, if you reuse some data you have computed on the GPU, would you keep moving things from the host to the device? Or? Yes,
yes. I think there is tremendous potential for performance improvement there by keeping stuff on the GPU in between kernel invocations. We don't do that at the moment, and again I think that's more PhD programmer efforts, because I know several papers have shown dramatic improvements from reducing that traffic between the CPU and the GPU. Yes, yeah. Thanks.
Why don't you just target CPU with the JITs?
Yeah, okay. So the number backend which we are using here to generate the GPU code does also target CPU as well, and we could do that too. And then that would give us 3 variants here to try. So we could have the CPU code and the GPU code, and also the interpreted code. And depending on the overhead calculations, we could run on any one of those. So yeah, that's an easy win. I think that's low-hanging fruit. Yeah, as another target backend. Yeah, yeah. In follow-up work, we have looked at the number CPU execution times, and again, there's this sort of crossover point where you start to win for